Hello, in this video, I want to discuss the central difference method, a numerical technique to approximate the derivative of a function. This is Norberto Trinidad, student of Math 221. Hello, in this video, I want to discuss to you about the central difference method, a numerical technique to approximate the derivative of a function. So what is a derivative of a function? Okay. Let's say we are given a function of x, and we have this function. And I want to get the derivative of it at point x. Meaning to say, there will be a tangent line passing through that point x. For example, this one. So this tangent line has a slope. And how can we determine this slope of tangent line if it is only a point that it is touching on our f of x? So therefore, at this particular point, we cannot have a slope. What can we do to assume that derivative at this particular point? So the technique is for us to have some small steps, for example, that we will assume from the original point x. And let us just say I have some small steps from original point x, and I will call this one as a step h. So therefore, this new point will be equivalent to x plus h. And my new point, which will constitute f of x plus h, okay, I will connect the original point x to that f of x, and therefore I can constitute a line with a slope, all right? But there will be error on the original tangent line that's supposed to be defining what is the rate of change at this particular point of x. So as you can see, this error will be smaller and smaller if we have our h step be smaller and smaller as well. And in this case, as you can see, I can step h forward. So I will have x plus h. And then also I can step h backward, so that I can have f of, I can have x minus h. And this will constitute some values in our function evaluated at x minus h. Now, doing these two will give us some error with respect to the original tangent line that defines the um, the rate of change at particular point x. But again, as we make the letter h smaller and smaller, we can arrive to the values of tangent line slope to be closer and closer, so that we can minimize uh, the error. So given the slope, as we all know, to be having the rise over run, and with this small step of h from the original value x, so we can define our slope to be for example, this point, which will be our rise, right? This is our original x point. This is um, our x plus h, and that will constitute a f of x. This one is f of x plus h. and the difference will be our rise. So there will be f of x plus h minus f of x divided by the run. And our run is our h, right? And I can also have another equation for the slope, which will be my f of x minus the f of x minus h, which will be my rise, right? This is my f of x, and this is my, let's say, this point is my f of x minus h, and therefore this is also a rise. But the formula will be my f of x minus f of x minus h, all right, all over h. So again, in these two approximation, we can have the approximation of tangent line at point x, and having the h values smaller and smaller will give us a closer and closer value to our tangent line and a very small error. So actually, these two approximation of the derivative has a name, and we can call it forward difference, and this one is a backward difference. Now, let us evaluate. So, for example, we are given an equation f of x equal to, let's say, x cubed minus 2x squared plus 3x, and f prime of x. We can easily differentiate this one. So we will have 3x squared minus 4x plus 3. And I want to evaluate this one at x equal to 2. And let us see, for example, I want to evaluate at x equal to 2. The derivative will be equivalent to 3 times 2 squared, that is 3 times 4, 12, minus 4 times 2, that is minus 8. 12 minus 8 is 4 plus 3, so this is 7. So let's say we have some approximation with h equal to 0.01. All right. And so let us perform the formula given in here. So f of x plus h, that is 2.01, minus f of 2 divided by h, which is 0.01. And the other one will be f of 2 minus f of 1.99 all over 0.01. Okay, so we will have in here, if we evaluate our f of x to 2.01, this will yield to 6.07041. And then our f of 2 is, if we evaluate this one, this will yield to 2, that is 8 minus 2 times 2, 2 times 4, that is 8, so that will be 0, plus 3 times 2, also that will be 6, of course, divided by 0.01, and that will be equivalent to 7.041. So all right, and that is our approximated value. So all right, that is our approximated value. Now, for this one, we have in here 6 f of 2, and f of 1.99 x cubed 1.99 x cubed minus 2 x squared 1.99 and plus 3 times 1.99. So that will be 5.9304. 9304. All right, divided by 0.01. And that will be equivalent to having 6 minus 5.9304, 6.96. So this will be equivalent to 6.96. So it is close to the derivative, which is at f prime having equal to 7. So that is not at least bad as part of our first approximation. Uh, but then again, this is forward and backward difference. So can we do some improvement to lessen the error? What will be the new method? Actually, we can. And the method to do that, to lessen the error, is what we call the central difference. As I've said, we have a central difference method that will produce a lesser error on approximating the derivative of a given function for any given point. For example, our point x having our f of x. So the derivative at this point is the tangent line that is depicted by our blue slope line. All right. And for example, I want to have an approximation that is a forward step. So from our original x, I will step forward by a value of h. So that will be a function of x plus h as a result of that step. And another one is to move backward by again an h value. So I will have a backward step that will produce a function f of x minus h. Now, as you can see, the error being produced of these two backward and forward step is in opposite direction. And actually, if I am going to get the average error of that one, I will have a new line that somehow, because of the average of that one, will be having, for example, this is that point, and this is the point that I'm getting through. Connecting that one will have our line much closer to the tangent that we want to assume. All right. So therefore, how can we get the average of the two? So we need to add the f of x and f of x plus h and f of x minus h, and then uh, of course the divisor will not be a value of h anymore, but it will be equivalent to 2h. All right. So so let us have a central difference method. Let's call it CDF. So that will be the average of this f of x plus h, all right, and f of x minus h. So that is the average of the forward and backward differentiation method. So we have in here, let's say forward, f of x plus h minus f of x, okay, over h, plus we have f of x minus f of x minus h over h. So, sorry, over h. So we will now have, we will cancel this one, and then what we will have is our x plus h minus f of x minus h all over 2h. And actually, this is the definition, the very definition of our central difference method. So a while ago, we obtained what is our f of x plus h, that is equivalent to 6.0741. Okay, I will just rewrite again our equation. F of x equivalent to x cubed minus 2x squared plus 3x. All right, and then my x is 2, and then my h is 0.01, and then our f prime of x, we said it is 7. And for the backward difference method, BDF, let's say, that is equivalent to 6.96. And then for the forward difference method, uh, right? So we have 7.041. So having this one, we will have, sorry, our f of x plus h is, let me erase. This will be, yeah, that's right. I'm sorry. This will be 6.07041 minus f of x minus h is 5.9304 all over 2 times 0.01. So, and that will be equivalent to, let me compute, 6 point, 6.07041 minus 5.9304, right? Divided by 2 times 0.01. So that will be equivalent to 7.0005. So as you can see, even on our forward approximation, we are having some kind of a good result, having h at 0.01, and as well as on our backward differentiation approximation, we have 6.96, almost close again to 7. But having our central difference method, CDM, sorry, we have this 7.005, very much close to our f prime of x that we used to derive manually and uh, obtain a value of 7. So therefore, our CDM is giving us a lesser error close to the value of the original uh, derivative of a given function. All right? So let us continue. For example, I want to discuss to you the error analysis of our approximation for the derivatives. So let us have this forward uh, difference method, and this one is our backward difference method. This one is our central difference method. So as you can see in here, this is the Taylor series equivalent of our forward differentiation method, or sorry, our f of x plus h. So this is the equivalent Taylor series. And from this one, we can derive the value of f prime. And then trying to get the value of f prime, we will end up with this equation. And f prime will be equivalent to our, ililipat lang natin, we need to transfer all of these except for the f prime. So we will have f of x transferred to the other side, this whole term will be transferred to the other side, and they will be divided all by h. So trying to uh, manipulate that, we will have in here f of x plus h minus f of x all over h minus this whole term divided by 1 over h. So as you can see in here, this is the definition of our forward difference method. And the term that we do not include, okay, in our computation is actually our error. Now, having this error term that we do not include performing the forward differentiation method, uh, we have 1 over h in here, and we have h squared in here, so there will be some cancellation. So h squared divided by h will just be h cubed divided by h will just be h squared. In this case, this first term will give us the highest value of error. And since it is governed only by h, all right, the h in here, it is governed only by h, so we will call this uh, um, error as an order of h. So the error for the forward differentiation method will be an order of h. Meaning to say, if the h increases by a factor of 10, our error will also increase by a factor of 10. If h is, let's say, lessened by a factor of 10, our error will also lessen by a factor of 10. All right. And let's observe also the same way what we have for our um, f of x minus h Taylor series. And after we define our value of f prime of x, so we can see in here that upon manipulation of this f of x minus h Taylor series, trying to get the f prime of x, which is our derivative, we will end up having the right side equation, the definition of our backward differentiation method. And again, um, we will have in here, and again, we will have in here this whole term, the remaining whole terms will be our error. And just like the f of x plus h Taylor series, getting the f prime of x, will have this error in f of minus h, getting the f prime of x will give us this error. And we have h in here and h squared in the denominator, the numerator, so we will be left by h in here, and this one is h squared. Again, as you can check, this term, this first term, will dictate the magnitude of error because it is the dominant, or the term that has the influence on the error. So, and we have an h in here, so we will call the error in here the same as order of h error. Again, if the h is multiplied by 10, our error will be multiplied by 10. And if our h is divided by 10, the error will also be divided by 10. So let us look, for example, how about the central difference method? So what we are going to do is to uh, have a difference of f of x plus h minus f of x minus h. So having said that, f of x plus h minus f of x minus h, so we will end up having the right side of equation to have 2h f prime of x plus 2h cubed f triple prime of x divided by 3 factorial plus h4 f fifth 5 prime of x divided by 5 factorial. So manipulating this one, if we want to get the f prime of x, we will end up having this right side of equation. On the right side of the equation, it is clearly, and you can see now that we have this formula which defines our CDM, or the central difference method. And then in here we have the error term. All right, on the error term, we have h squared, the first term that has the dominant contribution on the error. And therefore, the error for our central difference is an order of h squared. All right. So the error, which is dominantly dictated by this first term, will be an order of h squared. So what do we mean by that? If this error will be, for example, if this error will be multiplied by 10, okay, it will be divided by a factor of 10. Because, for example, if we have 0.1 and then we squared it, we will have 0.01. So that is the main advantage of the central difference method, because of the order of error is in a factor of h squared. Therefore, uh, if this h is being if this h step is half, it will give us uh, a factor of reduction in error by 2. All right, so there will be less error using the CDM method. So I think that would end up our theoretical discussion for our uh, central difference method, on why the error with central difference is much smaller than using the forward difference and the backward difference method, because of this Taylor series manipulation that we can have. And also graphically, as we explained, because of the trajectory of slope for having f of x plus h and having the f of x minus h, if we get the average, the resulting line and its slope is close to the tangent line, passing through the uh, some value of f of x where we want to evaluate the derivative. So again, thank you for listening, and I think this will end up my discussion about the central difference method. Let us now see my program that I made using Visual Basic to implement the central difference method. Thank you. Hello, sharing you the Visual Basic program I made to implement the central difference method. So as you can see in here, this is the Visual Basic form, for which, what is the central difference method, by the way? It is a method of numerical technique used to approximate the derivative of a function. And in here, I have 3 input boxes. And the first one is asking for the input function. The next one is asking for the value of x for which the derivative will be evaluated. And then the next one is the value of the step, which is equivalent to h. And as we all know, the central difference from the lecture is having this f of x plus h minus f of x minus h divided by 2h. So we need to declare this one to perform the central difference method. So let us check what is in the program. So first, in the program, of course, we will have this input user ask, And for example, we will evaluate x cubed minus 2 times x, maybe times x squared, and plus, let's say, 3 times x. So as you can see, my program is following some format. This is also case sensitive, like for the case of sine and cosine, the first letter should be in caps lock. And then for some polynomials with powers, you need to follow this pattern. All right, otherwise there will be exception error. Now, let's say we have this one that we want to evaluate, and that is, for example, I already type it in the calculator. So that is 7 when we evaluate. So let us check if our program can give us the correct answer. So evaluated at x equals to 2, and then let us have a step size of 0.0001. Okay, let's start. Now, upon clicking that button, we will now entering the main program, and we will enter on the central difference module, which has a function inside of it called central difference that calls the argument, the 3 arguments, the input function, the value of x, and the h. So let us now enter. And here we are in the module central difference, and we will do some parsing of the variables that is for the function of parsing. We can have it, and it's written all in the class, which I call function parser. All right, so let us get back. So I have a local variable y in here that I declared to be the summation of x plus h. So this will be 2.0001. And then the fx plus h, okay, having this x variable, all of those x's in that function will be replaced by y. So let us see if that happened. So now, as you can see on the original input that we have, so we have x cubed minus 2x squared plus 3x. So now all the x's are replaced by y. I'm doing this because inside the class function, there will be some error if I will be using only x. So I need to maybe introduce another variable that I can separate the result for fx plus h and fx minus h. All right. So after that, we need to parse that fx plus h value, which is we will enter now on the class and then find that parser. So again, in this class, we are declaring the expression that we have from that central difference module method, so that it will be consumed by the parser, and then try to evaluate what is the mathematical operation that we need to do with this expression. As you can see, the input function is in the text form, so it doesn't mean anything, and the Visual Basic or any programming language will not express it as a mathematical formula. So we need to parse it and then do some manipulation that will say, or will lead to the program what kind of mathematical operation for each term inside our equation is needed to be performed. Now it is still in y, which is a variable or maybe a character. It is not a number. It cannot be, processed by a mathematical operator. And then we have numbers, and then we have caret. This caret sign is still not understandable as some mathematical operator, as well as this uh, star sign, which is supposed to be a multiplication, is not yet understandable by the program. So we need to parse it and then perform some program manipulation so that we can evaluate it correctly, right? So I need to replace those y variables by a value, the value that can be understood by the mathematics operation, which is a number. So all those y will be replaced by 2.0001, which is our x plus h. All right. So after that, let's continue. The new string will now have the 2.001 instead of y. And I will now enter to a parse plus, for which I will separate all the terms by a delimiter of plus and minus sign. Okay, so this expression having negative and plus will separate these terms into three values, three terms. All right, after the split. So let us do the split, and we can see the splitted values into the array terms. On the local, you can check it. So again, we have eliminated or truncated the minus and plus sign. Now only the terms before and after that delimiter is retained, and now we are having these three terms. All right. So each of the term will be evaluated. For example, 2.001 raised to 3. What is the meaning of caret with 2.001 caret 3? It is still a text and cannot be understood by a mathematical operation. So we need to really again split this one and then have a snippet that will handle. If we saw this caret sign, it means we need to perform a power operation. If we saw this star sign, it means we need to perform a what you call multiplication, and so on and so forth. So, but one thing that you can see in here is after the split, the negative sign, which is a crucial one for the second term, is also eliminated. So I need to get it back and append it to the second term. Otherwise, we will have incorrect result doing the uh, what we call a derivative of central difference. All right, so let us get back. And actually doing that is uh, by executing this snippet. So as you can see in here, it is looking what index of terms did the negative sign be omitted. And if that index uh, has a negative sign that is omitted, I will append it back. So in here, in our expression, original expression, the negative sign is omitted on the second term. And actually, it is the zero index and then the first index. So the first index, I need to get back the negative sign. All right, performing that, you will see in here after performing that the negative sign is being appended back to the second term. So now we can evaluate this one. So this is still a text, nothing less, nothing more. So we need to perform a separation. Then we can convert the 2.001 and 3 into number type. Then we can perform the operation. So each term will be evaluated and see whatever mathematical operation it is asking. So let us continue. Now, after that, again, I'm sorry, uh, I I step on it and then just continue. Maybe I can demonstrate this same process, this fx minus h. It's just this one is fx plus h, this one is fx minus h. So but the parsing is no different. All right, so let us continue. So again, our expression is still in having this set. A while ago it is y. Again, I'm declaring some other variables for me to separate the fx plus h uh, evaluation to the fx minus h evaluation. So this set is still a text. I need to uh, replace it with number. So doing the same again, our expression now will be, of course, this is 2.22 minus 0.001. I will have now 1.9999. But again, I need to parse this one. So the same process. Let's split. Mm. Let's split. And then as you can see, I will have now the term uh, minus 1.999 cube minus 2.1. I already appended the same thing that we did on the fx plus h parsing. So, but I will not, I will not run and have a, uh, I'm, I'm going to add some breakpoints so that we will not be directly uh, executing this one, and then we will not see how the program execute the parsing for the mathematical operation that we need to do. So, all right. So first term, okay. First, our terms is now on this form, and I will have my ter to as an array to hold that term, and then uh, trim. I will just trim that term to make sure that there is no spaces or other maybe not necessarily characters. And then after that, I will convert it to double, the result to double. All right. So for example, let us step. So as you can see in here, the first term will be evaluated, but before I can get a numerical value on that, because it's still a text, the first term. All right. So I need to see uh, it does it contain this star sign, or I mean a multiplication sign, or does it contain this caret sign for a power operation? So since our term doesn't have this star sign, so it will not be evaluated by this function, but it will be passed through this function, and let us see if it can check. So if the factor contains this caret, yung parts natin, let's split. So now the parts will be splitted into 1.999 and 3. All right. So now that it is splitted, we have parts 0, index 0, and parts index 1 will be the base, and parts index 1 will be the exponent. So let us see what is the value of parts. So again, the base will be 1.999 and the power will be 3. So we need to introduce a math function, math.pow function, and evaluate that base and the exponent that we obtain, and then throw back the result variable. having that value. So again, this one is just uh, an ncalc function, a mathematical parser, but actually I do not have to throw it to this function, but just for the simplicity of the program, this one can evaluate the sine function and the cosine function and other mathematical operation. So throwing that function uh, equivalent for just a number, uh, it will just convert it to the number type, which has a double type. Okay. Now, if we do not, there is no, there is no, there is no complication even if we do not pass into this function the our expression now. I just need that result to be converted to, let's say, double. But all of the functions, I am throwing it into this snippet for for me to evaluate even the sine and the cosine. So yeah, so let us evaluate. So as you can see, the expression text 7.9990006 is now converted to double. All right, and will be now expressed as a number, not a text. All right. Okay. Continuing. Um, so let us evaluate the next factor. Okay. Sorry. Uh, the next term. All right. Let's evaluate the next term. And the next term is minus 2 times 1.999 raised to 2. Okay, so there will be two parsing that we will do in here. First is to parse this term uh, using a delimiter, uh, this star sign. So we will split our term into two. So as you can see in here, uh, the first factor, okay, is -2, and then the second factor is, well, which factor me? No factor. Uh, Let me continue. So because we are only doing an operation to a -2, so it will just be passed through our ncalc snippet function or for evaluate expression, and it will just be thrown back again as a number equivalent to -2. So the next one is our factor is now containing uh, a caret sign. So it will be evaluated, and after that we will throw it back to the, yeah, we will throw it back to the term that is the second index, and then multiply it because it will be thrown back as a number that can be interpreted after this one. Our result will be just a number. This is 1.9999 raised to 2, and then we will thrown it back to a result, and then after that we will get back in here. Okay, and then let's do the multiplication of the two factors. uh, the initial result is -2, then I will multiply it with this evaluated factor, which is now equivalent to 4, right? So now the result will be 8. -2 times 3.99999 something is almost 8. So After that, I will store it in the result. All right. And then evaluate again another term, the last term. So the last term that we have is the factor or the term 3 times 1.9999. Still, this is a text, so we need to parse it. Okay, it will be parsed by this snippet, and then we will evaluate. All right, and then perform the multiplication. So we have 3 times uh, 1.999, so it will just be I think 6. All right, so the result is now 6, and then so the result is now 6, almost 6. And then all of the terms, we will perform the needed operation. Okay, so now that we already parsed and evaluated, so we will have to uh, convert it into a number. Okay, and the number is 6. So let us. So we have in here the parse, the fx plus h is 6.007704, and then my fx minus h is 5.999. So I will evaluate it using the central difference formula, and then we will get the derivative function, derivative of the function. Okay. So now we have the derivative, which is equivalent to 7. From the calculator, as we entered it, we have a derivative of 7. So we have the correct value. All right. So again, if I input it, so I have the uh, derivative of the x cubed minus 2x squared plus 3x evaluated at 2 with step size of 0.001 is equal to 7, which is also equal to our calculator. Now, this calculator is using also the central difference method, but the step size is so small. I think it's a femto. Okay, one femto, or there are 14 zeros leading the one. So it has a very small step size, so that's why it's displaying 7. But nevertheless, we got the correct answer. Now I will just omit the breaks so that we can perform other derivative. All right. Let me omit the breaks in here, in here, here, in here. Okay. And then let's try to run the program. So let us say I made a mistake that I do not follow the syntax or the format. I made it small cap for the S, and then I want to evaluate is as 0.4, and then step size of say 0.1. Now the if I run the program, there will be some text that says, please check your input function and try again using the suggested format. So it means to say that there may be wrong in our format. So I will have in here S, and okay. So doing that, we will have our sine of x evaluated at 0.4 is equal to 0.91. Now, for example, I made the step maybe so small. And then if I evaluated it, that is 0.92. Anyway, so that is sine of sine x evaluated at 0.4, and I made a check yesterday that it has a correct outcome. All right. So how about for example x cube, and I want to evaluate it at 2. Let's say 2. So the derivative of x cube is 3x squared. So that would be at least 12. So let us see. So yeah, we have 12. All right. How about if I increase the step 0? So many. Maybe above the double range. Okay. So I think it's the limit of the double type. But again, we are, having correct value. All right. So that is a central difference method that I made using the Visual Basic program. Thank you.